Hi there, this is Yashwant and I work as an embedded software engineer at Analog Devices. Welcome to this video on designing a custom ARM Cortex-M based microcontroller for FPGAs. In this module, we'll discuss about integrating the Cortex-M processor into your design and sending a hello world via the UART. Let's get started. These are the learning outcomes from module 1. How ARM's business model works. What are the logistics involved in designing an ARM-based microcontroller? An overview of the DesignStart, Eval and Pro editions, architecture of a typical ARM-based MCU, block diagram of the Cortex-M1 processor, architecture of the Cortex-M1 based design for FPGA, block diagram of the Cortex-M3 processor, architecture of the Cortex-M3 processor based design for FPGA, the block diagram for module 1, how to get the IPs for the module 1. So these topics will be covered in theory and the upcoming topics in green will be covered in practice using the Vivado tool. We will discuss about the reset and clock control for the MCU, various processor configurations as per the need, the system bus or the interface used for the MCU, memory map of the microcontroller, the memory subsystem for program and data, the peripherals, debug subsystem for the design, the Xilinx design constraints file for the microcontroller design, software for the microcontroller, and finally deploying it on the FPGA. For the software, we'll be using the Keil MDK, the Keil Microvision 5 for this design. This slide explains ARM's partnership model. First, the semiconductor companies do a market analysis as to what's the requirement for their product. Then they look at ARM's product portfolio and decide which processor IP to use in their product. So first, they need to pay a license fee to get the IP and they integrate it into that design. And then when they finally fabricate the chip and they ship it to their customers, the semiconductor companies need to pay a royalty per chip sold to their customers. These are some of the logistics involved in building an ARM-based MCU. Based on the requirements, the semiconductor design companies choose different strategies in designing their products. They may use some of their in-house IPs for some parts of the design and decide to license out other parts such as the processor core. For ARM-based MCUs, the system bus would usually be part of the ARM bus specification such as the advanced high performance bus, advanced peripheral bus or the advanced extensible interface for high performance designs. These are some of the companies that licenses IPs to semicon companies. You'll notice EDA companies like Cadence and Synopsys are also there on the list. And these are some of the semiconductor design companies. They may choose either to use their own in-house IPs or license it from third party or do both. For instance, Analog Devices has products that use SHARC core for digital signal processing and also use ARM as a co-processor to run Linux. Semiconductor design companies decide whether to use their own fabs or outsource the manufacturing based on the process node that they need for their design. Semicon companies would often outsource fabrication for more advanced process nodes. These are some of the semiconductor fabrication companies. Note that I have not included companies like Qualcomm, Samsung, MediaTek, which are also semiconductor design companies, but they mostly target the smartphone market. And companies like Intel and AMD mainly makes SoCs for desktop and servers. Thanks to the DesignStart program by ARM, that now we can access their IPs for free of charge as part of their Eval program. Instant access to free use of Cortex-M1 and Cortex-M3 soft IP on FPGAs via simple agreement. We can use tools like Vivado to integrate the processor IPs into your FPGA design seamlessly. The DesignStart Eval package will take a proof of concept through to FPGA prototyping free of charge. And the DesignStart Pro package is free of charge up to the point where a company starts to ship silicon, after which a royalty applies. Now let's discuss about the two main microcontroller architectures widely used. On the left, we have the ARM Cortex-M0 based microcontroller system, which is based on the von Neumann architecture, where the same system bus is used for accessing both the program as well as the data memory. The Cortex-M0 is based on the ARM-v6-M architecture. This type of minimal architecture helps in reducing silicon footprint, thus reducing the cost and power consumption. This type of architecture is useful especially in battery powered application where low power consumption is crucial. Now on the right hand side, we have the Cortex-M3 or Cortex-M4 based system, which is based on the Harvard architecture, and it has separate buses for accessing program memory and data memory. This type of architecture offers a higher performance and can be used in time critical and soft real time systems. In this video, we will be looking at integrating both the M0 and M3 based systems into our design. This is the block diagram of a Cortex-M1 processor. It's based on the Cortex-M0 architecture with additional TCM interface and an obfuscated RTL. It's based on the ARM-v6-M architecture and implements the thumb instruction set. Has a 3-stage pipeline, which is the fetch, decode and execute stages. Has a 32-bit hardware multiplier. It has thread and handler modes of operation to run application code and handle exceptions. A nested vector interrupt controller, tightly coupled memory for instruction and data RAM. So this offers a higher performance compared to external memories as this is located closer to the processor core. An HB-AP with JTAG and serial wire debug support. This HB-AP master is the highest priority master in the HB matrix. And we also have breakpoint and data watch point unit support for debug. The target for the M1 based design is the AMD Xilinx Spartan-7 XE7S50 FPGA, and the development board used is the DesignStart RT-S750, which is prevalent among the maker community. These are some of the specifications for the FPGA design. Use a mixed mode clock manager for clocking the design, and then the processor system reset IP used for the system and debug reset signals to the processor core. And the debug is taken out via the PMOD interface available on the FPGA board. ITCM used to store the program, and we use the DTCM for the data memory. And an AXI3 interface to connect readily available IPs in Vivado. You can see we have an AXI interconnect here. A customizable microcontroller memory map, but we still have to adhere to the standards of the core, whichever is specified in the datasheet. The interrupt lines from the peripherals are connected to the NVIC. The ARM Cortex-M3 is based on the ARM-v7-M implementing the thumb instruction set architecture. There's a separate I-code and decode bus so that a literal data cache can be added on the decode bus, so that the literal data could be read even if the instruction fetch is stalled due to a wait state in the memory. The time when the Cortex-M3 processor was designed, the flash memory was pretty slow, and hence when the instruction fetch is still stalled, the data could be read from the literal data cache. We have optional MPU, memory protection unit, and wake up interrupt controller. We have NVIC and then tightly coupled memory, and most of this is the same as the Cortex-M0. We have an HB-AP with JTAG and serial wire debug, and additionally we have support for trace such as the ETM, ITM and the DWT. Target for the M3 based design is the AMD Xilinx RTX-7 XE7A100 FPGA, and the development board is the DesignStart USB 104A7. The specifications are more or less the same as for the Cortex-M0 based design for FPGA. On the left hand side, we can see that the system bus HP interface from the processor is used to access the DTCM, and any access that are not within the range of the configured DTCM is presented on the external system AXI interface. And this is the block diagram for the module 1. So the JTAG interface from the Cortex-M1 is taken out through the PMOD interface available on the FPGA board. The resets and clock controls are connected to the core using the processor system reset IP and the clocking wizard IP from logic core. ITCM is used for the program memory, TTCM is used for the data memory, and the AXI UART Lite IP from logic core is interfaced with the processor through the AXI interconnect, and then it is connected to the board via the external FPGA pins. Keil MDK is used to build the software. This ends the theory part. Now let's jump into the implementation. Search for ARM DesignStart in your search engine, and then head on to ARM. This will take you to arm.com/resources/DesignStart. Here you will find a tab saying FPGA designs and instant access to Cortex-M1 and Cortex-M3 IPs. Click on learn more. Scroll down to the download section, and here you will find the download links to both Cortex-M1 and the Cortex-M3 soft IPs. This is the download section for Cortex-M1, and this is the download section for Cortex-M3. You can go ahead and download both the IPs. Once you have downloaded and installed the IP, head on to Tools, Settings, and then click on IP Defaults. You will find a tab that says IP Catalog. Make sure that you have the ARM IPI repository for both the Cortex-M1 and Cortex-M3 added to this. So you can just click on this button and then browse and then just add these IP repositories, so that when we create a new project and create a block design, we would be able to access the Cortex-M1 and the Cortex-M3 IP from the search bar in the block design itself. For this demo, we will be using the Vivado version 2018.2. Please make sure to use the same version of Vivado, since the later versions of the tool has issues in synthesizing the Cortex-M IP. So we will go ahead and create a new project. Click on create project, and the new project wizard opens. Click on next. So give the project a name. I'll call it ARM-CM1 custom. So just point it to the actual project repository. So I'll create a project subdirectory as well. So check on this do not specify sources at this time, as we'll be using the block design and we'll be using the RTL project. Click on boards and then select the RTS750, which is the target for this project, and then click on finish. And now we have the project created. So once our project is created, let's go ahead and create a block design. Click on create block design and give it a name. We'll call this MCU top. Click on OK. Now here we can add the IPs and then add whichever peripherals we want. So first we'll start with the clocking engine for the MCU. This is the technical reference manual for the ARM Cortex-M1. So this section describes about the clocks and resets. So they mentioned that the processor has one functional clock input, that is the H clock, and the same H clock will be using to clock the interconnect, the system interconnect, as well as the peripherals in the design. So in the reference design provided by ARM, they have used 50 MHz for this H clock. So we'll be going ahead and using the same 50 MHz. So let's go to Vivado. So click on the add IP button and search for clocking wizard. So let's go ahead and customize this. So let the clock in be the sys clock. Sys clock is set at 12 megahertz for the RTS7 board, and we'll choose the MMCM, which is a mixed mode clock manager. So basically this consists of a PLL and phase shifter. So there are around 5 tiles in Spartan-7, 5 MMCM tiles in Spartan-7 FPGA. So input frequency is 12 megahertz for this. And let's go to output clocks. So let's go ahead and select the 50 megahertz for the output clock 1. We'll be using only one clock output, and we don't need the reset for the clocking engine. We need the lock signal, which will further be connected to the processor system reset. This lock signal indicates that the clock out is valid, meaning that the PLL is locked now, and the clock output, whichever is coming out of this, is valid. We have the MMCM settings here, leave it as it is, and this is the summary. Click on OK, and if you run connection automation, you will see that you can connect the sys clock to the board, the board's clock, which is the FPGA pin. Just click on OK. So this is our clocking engine for our microcontroller. So now let's go ahead and look at the system resets. Now let's look at the resets. So we have two resets coming into the processor. So one is the sys reset N and another is the debug reset N. Both of them are active low signals. So what I've mentioned is that the sys reset N signal resets the entire processor system with the exception of debug, meaning that when the sys reset is going on, it will reset the entire processor system, but the debug components which are present in the processor system, subsystem, won't be reset. Reason for this is when we are debugging the system and then when we issue a reset for the processor core, the processor core will in turn issue this sys reset request signal to the external system reset controller, and then this reset controller will reset only the core, because if we reset the debug subsystem as well, we will lose all the debug information. So this is the only logic that we need to follow, and we have a reference given by the ARM for the reset subsystem, and this is how it looks. So we need to use two processor system reset IPs. Reason is one would be extensively for the system reset request, which will be handled, and you can see there's an MB prefix here. So basically this processor system reset was intended for the microblaze softcore based systems, but we are just going to reuse it for our ARM based IP as well. So we have some logic here where the system reset request will be done either on the system reset request because of the debug, or the external reset as well, whereas the debug reset will be done only when there is an external reset which is connected here. And then we have peripheral reset, interconnect reset as well. These things will be going to the peripherals, whichever we are using in the design, and then this reset will be going to the interconnect, which we are going to use in our design. This is the processor system reset module, an example design given in their reference manual for the IP. You can see they have written microblaze plus interconnect plus IP subsystem. You can see clocks going from the clock with clocking generator, all the output clocks, and then we have one of the clock, the slowest synchronous clock connected here. We have only one clock in our system, that is 50 megahertz. So we'll be going ahead and connecting the clock output to the slowest synchronous clock here, and we'll also connect the DCM lock signal to this, and there's an external reset coming here, and you can see that there's an external reset coming because of not being debounced properly. You have some glitches in this signal, but the processor system reset kind of takes care of doing properly resetting the whole system. You'll see that initially the peripherals and the interconnects are reset, and there is a 16 clock cycle of delay finally before the processor reset goes slow. So we'll go ahead and implement this. And one thing to note here is that the reset from the board, RTS7 board, whichever is connected to the FPGA, is an active low signal. From this diagram we can see that. Click on the add IP and search for processor system reset. So we need two of them. Again search for system reset. So we'll name one of these as, just a minute, we'll name this as system reset, and then we'll name this as debug reset. Yeah. So there's a slower synchronous clock here. Since we are going to use a synchronous clock and only one clock, we go ahead and connect this to the clock here. Probably expand this, and then we'll go ahead and connect the lock signal. Now we have external reset in and auxiliary reset in for both the processor system reset IPs. So we'll have one external reset from the system reset going to the board. We'll just make it external, or probably we'll use the connection automation to do that. We'll just connect the system resets signal to the board reset. Just this. Yeah. So we have the system reset signal going to the reset. So when this happens, this reset would essentially reset the processor system as well as the debug components in the system, because it's an external reset. Whereas the reset which is present in the for the debug reset will reset only the processor subsystem. We need to have some more logic here. So when we add the ARM IP, you'll realize that both the sys reset and the debug reset are active low signals. So we need to have some NOT gates to kind of convert, but the microblaze reset is an active high signal. So we need to convert this into active low. We don't have that optional configuration in the configuration parameters for processor system reset. So we need to use a utility vector logic to achieve that, and we'll also concatenate combine the interconnect reset, asynchronous reset, and peripheral asynchronous reset using AND gates and give it. So we'll go ahead and use a utility vector logic. So now we'll choose this as R. The output of this will connect this to the system reset N of the processor core, which means this reset has to go high if either of the reset is issued, either the system reset N or the system reset request or the external reset request. So connect this, then we'll use another utility vector logic. You can simply Control C and Control V. You will get another IP as well. Go ahead. This we'll just name this as, that we'll do it later. This we'll use it for the, first we need to configure this 1 bit. This will handle the interconnect reset. This will handle the peripheral reset. And we also need 2 NOT gates. You can do a so we'll use this NOT gate to control the debug reset signal, which has to happen only upon external reset. So we'll connect it to this reset signal, and this NOT gate we'll use it for the system reset n, which has to happen on either of them. So we'll connect it to the combination OR of both the system resets. We'll regenerate the layout. So we finally have 4 reset signals coming. This is for the interconnect reset combined. This is for the peripheral reset combined. This is for the system reset n, sys reset n, and this is for the debug reset n. The 2 signals, external reset n and the auxiliary reset n, for the system reset request whichever is gonna come, we cannot leave them hanging. So we'll just pull it high because these are active low signals, so that they'll forever remain deactivated. We'll just search for constant. The constant value is 1, which is high. Just go ahead and connect both of these to this. So this kind of completes the processor system reset design. We'll probably rename some of these logic vectors for better understanding. I'll rename this as sys reset R. Rename this as for interconnect, right? Interconnect reset, and this will be peripheral reset, and this will be sys reset not. This will be debug reset not. Yeah. Now our now our reset and clocking subsystem is ready for our processor. Now let's go ahead and add the processor IP and connect these signals. Now that we have the clocks and resets ready, let's add the ARM IP. For that, first make sure that you have the IP repositories listed in the IP defaults. So these are my IP repositories in my desktop. Minimize this, click on the add IP, search for Cortex. So I have both Cortex-M1 and M3, so I'll go ahead with Cortex-M1. So now we have the Cortex-M1 processor in our block design. We'll go ahead and connect the resets and clock. So the H clock will be going to the clock out one, which is the 50 megahertz. So I'll just go ahead and connect that. And then, as we know, we have the sys reset going to the system reset not. This is coming from the OR. And then we have the debug reset, which will be going to the debug reset not. Yeah. And then we have the interconnect reset and the peripheral reset, which will be connecting them later. So at this point we have few other signals such as the interrupt signals, the non-maskable interrupt NMI, and then this is for configuring the ITCM, that is the instruction tightly coupled memory enable. So these bits will indicate the upper alias or the lower alias to use from the ITCM memory region, for the ITCM memory region. We'll go ahead and create a hierarchy for the reset and clock since the block design is getting too huge. Select the IPs that we have to include in the hierarchy. I'm just doing a control click so that I can select them. Right click and then create hierarchy. We'll name them resets and clocks. Reset and clocks. Yeah. Let's do a regenerate layout. You still need to connect the interconnect reset and the peripheral reset. We'll do that once we have the interconnect and the peripherals. We can't leave we are not going to use interrupts in this video. The next module we may probably be using them. For UART we won't be using the interrupt, so we'll have to tie them to 0 and not leave them hanging. Let's add a constant and put the constant value to 0, connect it to NMI, and also connect it to the IRQ. Even though there are 8 bits, probably in the auto generation when we do the synthesis it will change to 0 bits. It will concatenate all of them to zeros. And yeah, that's about integrating the processor. About configuring the ITCM enabled signals, we'll be looking at it when we are going to talk about the memory subsystem. Now let's go ahead and customize the ARM IP for debug. So here we have the basic configuration. We'll enable the OS extensions just in case we are going to use an RTOS for the software. Small multiplier and big endian, we'll probably not enable them as of now. And for the debug, let's select JTAG because we'll be using JTAG for in this video. And this is for enabling small debug. We won't do that. We'll just have the JTAG. And then we have the basic JTAG signals here. The TDO enable, the NT reset, the TDI, the TMS, and then the TCK. So we will have to make these signals external so that we'll be able to access them from the PMOD interface of the FPGA board. Let's go ahead and make all of these signals external. I'll just rename these. And for TDO and TDO enable, we need to have a tri-state IO buffer. Reason is in low power modes, the TDO enable will pull it low so that the pad won't be draining any current. So let's go ahead and add that. Click on the design sources and then click on add sources, add or create design sources, and let's create a file. Leave it the name as Verilog, sorry, file type as Verilog, and the file name would be try IO puff, and then click on finish. So we'll leave the module name as try buffer. Probably we'll paste the code whichever we need for this. Yes, yes. So I'm going to use a reference code from ARM for this. So this is just going to use some of the macros here, like the drive, the iBuff, low power, and the IO standard. These are specific to the FPGA. So in the diagram, we can simply drag and drop this module. Here it says that the module is already duplicated in the IP which we have installed. Just click on OK. It's fine. So connect the TDO to D in, and then TDO enable to output enable, and then make the IO pad external. This will be going to one of the FPGA pads. Just name this as TDO. These signals are sufficient for the debug. We'll later, when we discuss the constraints file, we'll give the constraints for the debug signals on the FPGA. Now, before we jump into the memory, we also have to connect the system reset request signal. This will be issued during debug. So we need to connect it to the debug reset processor system reset. Just take it and connect it here. Just do a regenerate layout. It's done. Now let's look at the memory. So here there's a tab for instruction memory and data memory. So instruction memory you can have up to 1 MB. We'll leave it at 32 KB itself because our program is going to be very small, so sufficient. For data memory, you have an option to select no DTCM, but we'll be using DTCM, so we'll leave it at 32 KB itself. But there's one more thing, we need to check the ITCM config ITCM enable bits what to be set. For that, I'll take you to the reference manual. This is the ARM Cortex-M1 reference manual. Here we can see that boot region when config ITCM enable 0 is 1. So we need to select this. If not, it is going to use if it's 0, it's going to use the DAP link interface. So this is a quad spy flash from which it can execute the instruction. So we have XIP, that is execute in place, available, enabled in this. So we don't want that. So if you have XIP, then probably it's going to fetch it from here. So we don't need that. We will be using ITCM. So we'll be setting the 0th bit to 1, and also the config ITCM enable, the first bit is always high for this example design, whatever they gave. So we'll also set it to 1. So the value that we have to give to this would be 3. 1 1 0 1 1 1 1 is 3. So we'll give the constant value of 3 in the design. So let's go ahead and add a constant. So constant width is 2, constant value is 3. Connect it here. So here you have an option to initialize the ITCM memory. We have to do that, but we'll give the ITCM initialization file as the hex file of the software that we build using Keil MDK. So we'll build the software, we'll get the hex file, and then we'll include it in the ITCM initialization file section. So that's about the memory. Now let's look at adding peripherals. AXI is advanced extensible interface, and it's a little different from a regular system bus because it needs an interface, so it's not a bus technically. So we need an interconnect to actually interface another peripheral with the processor. So we'll go ahead and add an AXI interconnect. So here we have an AXI interconnect. So we have configurable number of masters and slaves for the interconnect. So we'll configure both as one. The one AXI master is the processor, and the one AXI slave is going to be our UART peripheral, which we are going to use. So slave interfaces, we'll just leave it as default. Click on OK. There's a connection automation, but we'll probably not do that because Vivado actually handles connection automation based on the microblaze softcore processor, but this ARM IP, so it messes up with the reset and clock signals because it assumes one processor system reset to be part of the microblaze software. So we'll probably not do that. So directly connect the interconnect, and the clock will be same as H clock. We use the same clock across our designs. Connect it to the H clock, and now we have the reset. So this reset should be connected to the interconnect reset, whichever signal we had. Probably expand this. So let's connect it. This one. And then connect all the clock signals to the same H clock, and the reset signals to the same reset, synchronous reset. And inside, if you expand this, you'll see that there's a coupler, and probably we just have one interface, so that's no problem. But if you have multiple peripherals, you will be having an AXI crossbar, and then we'll have one slave interface and multiple master interface through a AXI crossbar. So this is for the interconnect. After we add peripheral, we'll configure that in the address editor here. We'll assign an address for the peripheral, which we'll be using in our software. Now next we'll look at the peripheral. So as we had looked at the block diagram for module 1, we'll be using the AXI UART Lite IP. It's a very simple UART implementation and uses very little logic. So here we won't be using the interrupt, but let's do one connection automation before we go on. We'll connect the UART signals to the board's UART, so that this will go to the RTS7's UART. So there we have an FTDI converter where we'll convert the USB to serial, so that we can directly view the output whenever we send something from ARM through the UART. We can view that output on our system itself using a UART serial terminal. Click on OK. Now connect the slave interface to the master interface, and then connect the clock again to the same H clock, whatever we have. And the reset should be going to the let's try to configure this. If we have, yeah, okay, we don't have any configuration as such. Let's expand this IP. So let's connect the reset to the peripheral reset. Yep. So now we have connected all the reset signals, peripheral reset, interconnect reset as well. I'll minimize this, then I'll do a regenerate layout. Yeah. Now let's go to the address editor. Here there is an unmapped slave, so click on assign address. We'll leave it at this address. So before deciding that, let's look at the memory map once again from the technical reference manual. This is the memory map. So we have our ITCM lower alias selected. So the code region will be at 0x 4 zeros and then 4 zeros. And then we have our DTCM selected as well. So our data memory will be at 0x 2000 and then followed by 4 zeros. And for peripherals, this is the memory map of the reference design that they have given, but we won't be using that. So our peripheral is residing somewhere above this, but it's still within the range of the peripherals memory map. So we have UART selected. So it is in the allowed memory region only as per the Cortex-M1. Later, if we use block RAM, that will have this memory region, but we'll look at it later. And these are some of the registers that are accessible from the private peripheral bus. So they have a different memory region. Coming back, so we have this address assigned, which is permitted. So this completes the block design more or less. Let's go to the sources and let's create a HDL wrapper for this. So right click on this and click on create HDL wrapper and let Vivodo manage wrapper and auto update. So this will suck in the dry state IO buffer. Okay, we have a warning here. I think there's a mismatch in the logic states. Oh yeah, this has to be just one bit wide. By mistake we had given 8 bits. Yeah, okay. Save the design. So I think we have the wrapper created. Before moving on to synthesis, let's make sure that the configuration is all fine. You can still do the synthesis without giving the initialization file. We'll probably give it later once we build the software. We just have to do the synthesis again for this because it kind of fetches the initialization file during the synthesis step itself. Let's go ahead and we'll minimize this, then we'll run synthesis. Save the project, yes, save. I can run 24 jobs based on your system capabilities. You can select the number of jobs you can host. Select the maximum to complete the synthesis as fast as possible. Click on OK. Click on design runs to see the synthesis running. Suppose it will be running the out of context module runs because we are synthesizing the design for the first time. For incremental additions, it doesn't have to run all these, but for the first time it has to run all these designs. You'll see that this is the Cortex-M1 IP, so it will take quite some time to run the synthesis. See the notifications coming here. You can also see the usage, number of LUTs and flip-flops for each of the component in our design. Okay. I think all the runs are done. synthesis completed successfully. So we won't be running the implementation. We'll have to look at the constraints file as well. Just click on cancel. Next, let's look at the constraints file for our design. Now let's look at the constraint files. We'll have two constraint files, one for timing and one for the pins. So we'll create file, we'll call it timing s7.xtc. So it's timing for the Spartan-7. So timing, and one more file, we'll call it pins s7.xtc. Okay, and finish. See, I already have the constraints file, so I'll just paste it here. So this is the constraint file for the timings. We also have the pull-ups enabled for the JTAG ports. We probably don't have this one, so we'll just remove this. So this is just for the JTAG ports. We have the NT reset, the TDI and TDO. Then we have the delays, maximum delays and the minimum delays for the system clock and the TCK for the DAP. The output delay and input delay, we have a few things here for the JTAG, and here we have the reset listed here. And then for the pins, I'll be just using the master's constraints file. So this is the master constraints file. If we look at the block design, we'll see we have the 1, 2, 3, 4, 5, 6 inputs and 2 outputs. There are 2 pins in the USB UART, but yeah, so all these pins need all these inputs and outputs need to be mapped to the FPGA pads using the constraints file. So here we have the sys clock and here we have the TCK. So this clock dedicated root false is needed because TCK is essentially a clock pin, and this is needed to suppress some of the warnings in Vivado. This will kind of fail the implementation if we don't use this. And then we have the this is not needed, so I'll just remove this. Yeah, so here we have the TMS and TRST, the TDI and TDO, which are there here, and then we have the UART and RX. Even without this also, we have the board constraints which will take care of mapping it to the right UART pins on the FPGA, whichever is connected to the FTDI, and we have reset here finally. So these pins, we can do this mapping by looking at the manual. I'll just open the RTS7's reference manual. This is the RTS7's reference manual. Here we can see the FPGA pins for the PMOD JC. We'll be using PMOD JC because that is much closer to the FPGA on a physical level. If you look at the board, you will realize that we have a picture of the board here. You will see that the PMOD JC is much closer to the FPGA based on the PCB routing compared to the other PMODs. So to kind of have better timings, we'll use that. And we can also look at the pins for the reset and all. So this is for the UART. You can see Spartan-7 V12 and R12, the FPGA pins connected to the UART via the FT 2232 to the micro USB. So we'll have both UART as well as the JTAG being exposed as COM ports on the micro USB via the FT2232, and then we see reset is connected to the C18 pin of the FPGA. So this is how we write the constraints. This is a master constraints file. I've simply edited so if you put a hash, it becomes a comment. So I've just edited them and I've added the constraints. So let's go ahead and save, and then let's click on run implementation. Click on yes. Okay. So the implementation has been completed. We don't have any errors. So before generating the bit stream, we might have to build the software and add the hex file into the ITCM section where we had the. So we'll just open the implemented design and just see how it is. Have the utilization also listed here. So this is the implementation. So we have a lot of logic left to implement other peripherals, maybe probably a crypto engine or so. Otherwise we have there's very little utilization. But if we implement a Cortex-M3 on the Spartan-7, then probably it's gonna utilize a lot of logic here. But yeah, otherwise we have a lot of logic left here, and we just need to just run this. In the block design, yeah, we need to add the program memory into this to print something via the UART. Let's say hello world via the UART. So now let's look at creating a Keil project and then doing this. Let's look at the utilization. So we fairly small. We have 3024 LUTs and 2728 flip-flops used, and then worst negative slack and the total negative slack seems to be fairly decent. But let's see after the bit stream generation as well. Now let's create the project for the software. So I'm going to use Keil microversion for this, and the version of Keil is version 5.26 that I'm using. So let's go to project, new microversion project, give it a name. So I'll give it CM1 custom CM1 software. Cortex-M1 is based on the Cortex-M0 processor only. So we'll select Cortex-M0 as a target. In KIMSys, we'll select the core, and then we'll set on device, we'll select startup here, and then click on OK. So this will create the project, and now we'll create the main.c file. Add new item, have the main.c file, as well as we have the startup files where we have the stack pointer, reset handler, and the basic stuff here. So basically here we have the reset handler. I'll just go there. Yeah. So here we have the system init being called first, and after that we have the main being called from here. So it will come to main in this file. So before we can write anything, let's see if we want to print something via the UART to the serial terminal of this desktop. We need to write a very basic driver for the UART, or maybe a simple software, few lines of code to write it into the UART buffer from the processor core. So now let's look at the logic core IP whichever we used in our design. So this is the manual of the UART light IP whichever we used in our design. So this is the block diagram. We have the AXI interface. We have a receive data FIFO, transmit data FIFO, a status register and a control register. So we will basically be writing our buffer into this transmit data FIFO so that the UART will transmit it via the TX pin, and we'll receive it from the serial terminal on the desktop. So what we'll do here, let's look at the register space. So this is a very simple implementation of UART. So we have only 4 registers in total, one RX54 register with offset 0, one TX54 register with offset 4, one start register with offset 8, and one control register with offset 0C. So in control register we have these bit fields: reset TX54, reset RX54, reserved and interrupt. Interrupt we won't be using because we have not connected the UART's interrupt to the core, so we won't be using interrupt in this module. In upcoming modules we'll use. In start register we have RX54 valid data, RX54 full, TX54 empty, interrupt enable, frame error, overrun error, and parity error. So we'll basically have to write the data, and then we have the TX54 and RX54. So in TX54 just have to write it into the 1 byte into this 8 bits 8 bit fields here. So we'll first what we'll do is we'll just simply reset the TX54 when we start the program, and then we'll write it into we'll write the ASCII value of the letters which we are going to send here in the TX data, and then the status register we'll wait till the TX54 is empty, and then we'll write the next byte into the TX54 again. So we'll do that till all the bytes are being sent out. So first of all, let's go ahead and create the type def. So we'll first include stdint.h, and before that we need to configure some few things here. So we know that we are using 32 KB for ITCM as well as the DTCM. So 32 KB is equal to hex 8000. So we can do a quick calculation if we want. So 32,768 is equal to hex 8000. So the same thing would apply for data memory as well. Starting offset is 2000, but the size is just 8000. And output we need a hex file. So we'll create hex file, listing user. So we need to configure this. We'll do that once we have the software built. When we are able to build it, we'll do that. And this we'll just uncheck. SM is fine. Then linker we need to give one miscellaneous control. So we need to give entry as reset handler, and check this use memory layout from target dialog, which means from this target dialog we'll use this as the linker for building our project, because this is the address which we are going to use. This is for the code memory and this is for the data memory. Using ITCM and DTCM. Then debug, just select JLink and just make sure that you don't have any flash programming enabled here, and click on do not erase, because the hex file which you are going to build will be included with the bitstream, and when we what we are going to do is just a debug, and then we'll just debug the code from the core via the debugger. We won't be programming anything through JTAG. So that's it. only the creation of hex file, that alone we'll look at it later. That we will have to do after build stuff. So let's go ahead and create the type def struct. So in total we have 4 registers, each of 32-bit wide. So what are the 4 registers? So in total we have, let me look at the, yeah, Rx, we'll just name it Rx, Tx, stat and control. Rx, Tx, stat, control, and we'll name this UART type def. T underscore T means type def, and we'll just dereference these in the order. So let's just do a hash define UART base address. This UART base address, so the address of the UART peripheral, that we'll get it from Vivado. If we go to address editor, this is the base address of the UART. We'll just copy this. This is the base address of UART. Yeah. Then we'll do one more hash define. This will be the pointer we'll be using. So UART type def T. We'll just dereference the pointer as the UART base address. Now let's define an instance for the type def. It's a pointer. We'll just have a simple prefix, and we'll print a simple hello world. So the string hello world has, let's see how many characters it has. So in total we have 1 2 3 4 5 6 7 8 9 10 11. So we'll just put 11. So we'll just put int main void so we know what needs to be done here. We just have to clear the TX54 register first. So if we go back, TX54 is the 0th bit, so we'll have to clear it first. So PUART, sorry, control, that is the 0th bit, so 1 shift by 0. So this will clear the TX54, clear the TX54. Then let's have a loop for equal to 0. We have in total 11 characters, so I less than 11, I plus plus. I'll just declare it as a global variable here. And what we'll do inside the for loop is, we'll just write the value of the string into this. I mean, this will basically be 1 byte. Character is just 1 byte. So each byte we'll just write it into the TX54. But TX54 is 32 bits, so we just have to make sure that what we are writing is only 1 byte. So, and with 0xFF, this we'll write only 1 byte into this. So we'll so now that we have written 1 byte, just add that comment as well. Write 1 byte character into TX54. And now that we have written 1 byte, we have to wait till the TX54 is empty. So if we look at the manual in the stat, so the second bit 0, 1, 2, the second bit is the TX54 empty. So we have to wait till the TX54 is set. So it means here we have empty. So 1 means TX54 is empty. So we need to wait till it is set to. So let's do that. Wait till TX54 is empty. So UART, we'll just put a while loop here, while not of UART stat and with, so the TX54 empty was the second bit, 1 left, shift by 2 more, yeah, and that's it. So once this is done, probably we'll just have a while one. We can't return from main, so we'll just have a while one. That's infinite loop. So this is the software that we need to use. So this is pretty much it. Now for the build, we need to configure something else. When we build this, let's try to build this. Yeah, we're able to build this. So the hex file that we get out of this essentially has lot of other things, like for example, I'll just quickly show you the hex. So this is objects, this is the hex file. Try to open it with notepad. You'll see that we have it's an Intel hex file format. So you basically have the address, you have the offset, you have some CRC and all those things. We don't need all of this to be going into the Cortex-M1's code memory. So we need to have a script that would essentially convert this to the SRAM memory. I mean basically the BRAM memory format. So for that, ARM has a script, and I have it here. I'll probably show you what the script is. So the script basically calls the from elf, and then these are the parameters. So we pass the AXF file from the objects as the input, and then we create the hex file. So I've just named it itcm1, so it goes into the itcm.hex. So this from elf, this is part of the Keil microvision tools only. This is an executable. So I'll just show you where this executable resides. So if we go to C drive, Keil, ARM-cc bin, here we will see from elf here. So make sure that this path which we have here, that is part of the environment variables for users. So I'll just show you environment. Yeah. So let's look at the path. So here make sure that whatever path we have here, ARM-cc/bin, so that is added here, so that it is recognizable from the script. And let's also look at the hex file that we had. Keil. So the name of the hex file is so the name of the AXF file is this. So we'll just give it here. So this is the AXF file and this is the name of the hex file which will be generated. So let's add this as part of the post build in Keil. Let's go to settings, output, that is fine, user, and we'll just select this script and let's click OK. So that now if we build this, we'll see that this command is executed and this output should now be present in the directory. So here we can see that we'll have yes, we have the ITCM1 hex. If we open it with notepad, we'll see that all these things are gone. So it will start directly from the just the instructions. So we just have the address and just the instructions, whichever. So this will essentially be the stack pointer, and then we have the other instructions here. So now that we have this, we can copy this and put it in the directory where we have our Vivado project. Go there. So I'll just paste it there, and now we'll go to Vivado, and as I mentioned here in the instruction memory, check initialize ITCM, and then the name of the hex file was give it here, click on OK, just do a regenerate layout again, save the design, and then now let's click generate bitstream, yes, click OK. So the bitstream generation has been completed successfully. Click on OK. Now I've opened the hardware manager, click on open target, click on auto connect. You'll see that we're able to detect the FPGA. I'll just show you my setup quickly. So this is how my setup looks. I have the RTS7 FPGA, connected the debugger signals to this, the debugger connections, the TDI, the TDO, TMS, TCK and NTRST from Xilinx debugger to the PMOD JC connector to the RTS7 FPGA, and then I have USB connected, and through this FTDI we can program the FPGA via the JTAG as well as also use the USB to UART. Please note that the JTAG that we are using here is to actually program the FPGA. This is a JTAG of the FPGA, while this JTAG we are using is actually for the core present inside the FPGA. So that's the difference. So right click on this and click on program device, and we have our MCU top wrapper.bit, whichever was the top wrapper Verilog file there. So just click on program. So now this is program. Now so here I've opened the Keil window. I'll go to the debug window, and we can see that the debugger is able to detect the ARM core site JTAG debug port here. So the max clock is set at 5 MHz. Make sure that you don't have any flash programming options selected here. Click on OK, and it already printed once, but we can still go ahead and debug this design. So every time a reset happens, it's just printing hello world. So you can just run it and it prints hello world here. So this is the example design for Cortex-M3. So basically we have lot of options here, like the optional MPU, configurable priority width, the wake up interrupt controller, bit banding, and then a lot of options for debug. Like we have trace options like ITM, ETM, and you also have DWT, and more or less the other things kind of remains the same. And you can similarly the same way we have JTAG signals taken out, so you can attach a debugger and debug, and also we have the UART late IP and the address. So you have two buses here, that is why that is shown here, but more or less this also kind of works the same way. So that's about it for this video. Thanks for watching.